Good morning, everyone. It's now 1:30. So I think we'll get started with this morning's webinar. Firstly, just good morning to everyone, and thank you for taking the time to join the webinar this morning on laser scanning best practice for forensic collision investigators. The webinar should last around 30 minutes to 45 minutes, depending, of course, on questions that you may have. I will have spoken to a number of you or met you on a number of occasions. But for those that don't know who I am, my name is Mike Skeetskill, and I'm the Business Partnerships Manager for Leica Geosystems, with a particular focus and interest in collision investigation and in the development of our long-term engagement and relationship with UK Police. I'm also joined this morning by Chris Gibbons and Dr. Kate Strange, who between them have over 30 years of experience in laser scanning and surveying technology, and they will guide you through the typical RTC or road traffic collision scenarios in urban, semi-rural and rural environments, and also discuss the various considerations that need to be taken into account when using a laser scanner in those environments. As you know, I think we've worked very closely with UK Police over a number of years. Many of you have Leica products, but I must emphasise that this webinar is very much manufacturer agnostic and simply looks at best practice when looking at the use of laser scanners in those different environments. As an organisation, Leica Geosystems is the only survey instrument manufacturer who are approved development partners of the Chartered Institute of Civil Engineering Surveyors and a corporate member of the UK Survey Association, otherwise known as TSA. So whether you're new to laser scanning or an experienced user, this webinar, which, as I said, is manufacturer agnostic, is very much designed to provide a best practice look at the use of laser scanners in different locations in line with the Survey Association's laser scanning best practice guidelines, and is presented by two very experienced and knowledgeable qualified surveyors. The webinar forms part of our process of ensuring that all collision investigators have a good working knowledge of laser scanning, and you're probably aware of the work that we've been involved in, both with Richard Ottey from Metropolitan Police, who's leading on the Forensic Collision Investigation Network on laser scanning. We have been putting the documentation together that's gone through to UCAS, and we're just putting the finishing touches to that at this moment as we speak. And this is all linked with the Forensic Regulator's recommendation for accreditation by October 2020. So we're all working towards that goal, and this is part and parcel of that process. So I'd now like to pass you over to Chris and Kate to take you through the webinar. If you do have any questions, at the bottom right-hand side, there should be a question mark. You will be able to post any questions to the site, and at the end of the webinar, we'll try our very best to answer them then. Okay, Chris, if I can pass over to you, please.
Thank you, Michael.
Sorry, Chris.
Okay, good morning, everybody. Some of you may know me. My name is Chris Gibbons. I'm based in Northwest England, and I've done quite a bit of work with a number of police forces in my region, most notably Lancashire and North Wales. What I'm going to take you through this morning is just to go through three scenes, which in the environment they're in are completely different. But the crash scene I've tried to create in the drawing diagrams that I'll go through are the same configuration of vehicles and crash, and just really a look at how we fit the scans together so that we get one complete point cloud which we can take forward and have confidence that it is going to be usable data. So the first scene that we look through, if you could move on for me, please, Mike. This is an urban scene, so it's a street scene. It's a busy road going through a shopping parade, and as you can see here, there are a number of solid structures around us, from bins, buildings, buildings going off down side streets, signposts. Not only are they, the solid structures going all the way along, but they're giving us surfaces which are going off in different directions, which, as Kate will explain to you later, become a very, very important, play a very important part in fitting the scan scenes together. So as you look at this scene, this is a scene really where what you will get, regardless of where you put your scanner, there is going to be a considerable overlap of bits of surveyed structures which may not be part of what you're actually interested in, but will go a long way to helping you give you confidence that this data is going to be correct. So as we could move on, in the next slide, this is the first scene. So as you can see, we've got the lamppost denoted by the circles going along the side of the road. We've got a couple of building faces. We've got one of the side streets showing with the building corners in, and in the middle of the street we've got the start of two vehicles which have crashed together and some tyre markings. Okay, so we do the scan from the first setup, and we collect the data that we can collect from there. On the second setup, we move the scanner to get the vehicles from a different direction. But the surrounding area, we will get the same information again, the same surfaces, so the same lamppost, the same building structure. And I notice on the south side of the road towards the western end, it doesn't get clearly because there's no line of sight. There's the side street on the wall. It's remained green, so because we haven't managed to get that data. But most of the rest of that scene, we've got a lot of overlap there. So on to the third scene, we move around this crash scene again, and we can then start picking up more bits of the scene. And as you can see, the scene is holding together, and we're getting a very clear picture of the scene with all the structures and all of the points of interest being held together with confidence. And finally, the fourth setup to surround the scene. Okay, and there we go, we've got the same structure. So what we're using here to give us that confidence that this scene all fits together, and as I mentioned, the tyre marks may be a crucial piece of evidence, and I'll keep coming back to those tyre marks as we go through. Those tyre marks are following the same course on all four setups, so we know that piece of evidence is going to be a usable piece of evidence. Okay, so the next scene that we move on to is maybe not quite as easy, certainly not the perfect scene for laser scanning, but certainly a manageable scene with how we can work. So again, there's considerable overlap from wherever we set up. There's the crash barriers through the central reservation, there's the bridge in the distance, there's a few lighting columns available, and maybe at the top of the embankment, although they're covered in vegetation, there may be fences, bits of fence that are showing through, and maybe street signs, signposts that we can utilize. And these again are surfaces which are not only are they at different heights, but they are going in different directions as well, which will help us to again manage those scan setups and fit them together. So again, as we go through the scene, so again we've got the same setup. So I've denoted a few of the bushes on the embankment to show the vegetation. We've got the embankment going up. Rather than having a central reservation, I've got the fence at the top of the embankment, and we've got the bridge in the south eastern end of the survey. We've got the bridge going across, and those features, you should be able to get large amounts of those features from wherever we set up. So again, as Mike, if you can move on to the through the setup. So again, setup number 2 overlays very nicely. Setup number 3 again will overlay very nicely, and those tyre marks again, potentially a crucial piece of evidence, are all lined up in a line where we can use this. And finally, the fourth scene. So we've managed to get the whole crash scene, but again, we're using all the surrounding area to pull that data together. So our final scene, and this is what I would say is much more difficult. I've called it worst case scenario, and the reason for that is, as you can see, is all you can really see, apart from the road surface, which is a good solid surface, which is going to give us some confidence in the height of our scene. There's not a lot of hard detail that we can then, which will be picked up in the scan overlaps, which will allow us to fit those scans together. Now on this scene, I've actually zoomed in on the screen just to see what there possibly could be. So on the first zoom in, on the next slide, please, Mike. Thank you. I've circled a signpost in the distance. That's quite some distance in the distance from where the scene is. You may find that it will be picked up on some of the scans, but maybe not all of them. So it may help a little bit in getting you a starting point and a reference to an angular reference to orientate your scans. On the second zoom, again, there's another signpost in the distance, in amongst the trees again. There's no guarantee, depending on where you put your scanner setup, that you're going to pick up that with any any great certainty there. And then on the third setup, we don't have anything other than vegetation. Now, vegetation for the surface, there are a lot of surfaces, but depending on the angle that the laser scanner is hitting those surfaces, it's not really going to create a good surface for us to be able to fit that together. And then on the fourth surface, we've got one little fence post in the verge that we could potentially use as a marker to help us orientate the scans a little bit. But again, no guarantee that anything will really work there. So as we go through the setups now, this is a potential that could happen. So again, we've got the same configuration of vehicles with the tyre markings. We've got the vegetation along the side of the road. The second setup, now because we've got so little hard detail, the only thing that we can use in a cloud-to-cloud registration here are the vehicles themselves. Now, even though between these two scan setups, it looks as though the vehicles have tied themselves together very well. As you can see, a slight orientation error within that small area will then magnify itself as we extend out from that area. And you can see the end of the tyre marks and indeed the sides of the roads are deviating away from each other as we go along. The third setup, we could potentially have the same problem. And then the fourth setup, again, we could have 4 scans, which although anchored in the same place, could have very slight orientation errors. And of course, in this diagram, I exaggerate, but you can see clearly the result. If these tyre markings on the road are a crucial piece of evidence, which is correct, and is this something that we can take and utilise as evidence in a court? There is a way around this, and this is where we use the targets I'm going to use the word control the orientation of this scan. Now, as you can see, targets are not really necessary in every single scene. They're something that are a backup for us in the worst case scenario, and a useful tool to have in your vehicles to utilize in this. So in this situation, if I was doing this scene, I would put out a series of targets. If you move on to the next slide, please, Mike. And so what I would do is I'll put targets around the scene in areas where I'm going to be able to pick them up from all the setups, and I would surround the scene. So the way that targets will work for us in this instance is they will create a vertice in space at multiple locations, and that will allow us then to do a transformation between one point cloud and the next point cloud from the multiple setups, and bring those scans together. And that will then, as well as help the anchoring point, but it will also help the orientation of those scans and allow us to have a scan scene, finalized point cloud that we have got confidence with, and we can take forward to use for the task in hand. So that's my very, very quick and brief run through some potential scenes that you may see or come across. What I'm now going to do is hand over to Kate, and Kate is going to explain the science behind how both the cloud-to-cloud and the targets work and aid us in giving us a point cloud with confidence. So thank you very much for listening, and I'll hand you over to Kate.
Hi, hope you can hear me. My name's Kate, and I'll take you through a little bit about what happens under the bonnet in the black box of Cloud to Cloud. If we can move on, Mike. So how does it work and when doesn't it work? So how do we get it to be from that separation to come together? That's lovely, thank you. And if we move on, we'll have a look at the information that we actually need to have within our scans in order to do this cloud to cloud alignment. So obviously we have our X, Y, Z values of our individual points, but we also have the order that those points were scanned in. And this means we can figure out which are their neighbouring points, and from that information we can calculate the normal direction of the surface. And this might be a term that you've not heard before, but it just means the way that a plane is orientated in 3D space. So if we take a look at our simple corridor and building example, so I've taken like a floor plan here. We can see we've got a setup 12, which is out in the corridor, 13 in the doorway, and 14 within the room. I've indicated the normal direction of those surfaces with the coloured arrows, the colouring of the arrow coming from the scan setup to coincide with the colouring of the point cloud information. So you can see the idea that the planar surface of those walls, their normal direction faces into the room. And if we look at this, the room compared to the corridor, obviously that room wall is very close to the corridor wall, but the surfaces of them should not come together. Although they are close, their normal directions indicate that they are completely different surfaces. So we don't pull those ones together, we allow those to sit apart, having the thickness of that wall. And if we think about this in more of a 3D way, we'll take a look at the corner of the room. If we can have the next slide, Mike. So if we just look at the corner of the room, you can imagine the normal direction coming out on the wall below the window with a nice big arrow showing its normal directions for the walls, for the floors, for the ceilings. So that's what your normal direction is. And we use that to align them together. So once we've got that information, we can then move our 2-point clouds together so that our points are in the same plane and the normals are in the same direction. And it's an iterative process, so we move it closer and closer together, looking at the statistics all the time as we go to try and get that to converge to a single constrained outcome. However, not all overlap is the same and not all surfaces are equally helpful. So here we have the primary singular surface where we have effectively lots of points, but one surface and therefore also one normal direction. So we bring our secondary cloud in its initial alignment, and then we start our cloud-to-cloud alignment so it moves to become in line and facing in the same direction, and it fits, which is great, but it fits in multiple different places. So we can't have confidence in our outcome because this is a slippy surface and our results would be under-constrained and it would rotate around. If we then take that on to the next level, sorry, my apologies. So the real life situations which would be akin to this sort of planar, singular planar surface are your rural situations, a nice open beach, or even something you might consider more industrial but is equally flat. So it's about getting away from considering it just being rural or semi-rural to understanding what's in each individual situation. It could be an airport, which you wouldn't necessarily say is rural. If we take that on then to our next level up of a perpendicular plane on our first plane, again, we can bring our second cloud approximately in line. It does its optimization, but again, it's still slipping along that kind of fold axis, and we can't have confidence that the results we would get out would be correct because it would sit in multiple different places. Again, it's under constrained. It's better constrained, but it's still under constrained. And we have that horizontal slide within it. Now, these sorts of situations would be akin to a cliff and a beach, or a railway cutting, for example, or even a tunnel. There are obviously more sides in the tunnel, but that same central slip is still there for that one. So what we actually need within our overlapping scans are 3 directional planes, so that we've got normals going in 3 directions. We can bring them together, and when they do come together, they actually can only sit in one orientation and position. So we are confident that wherever we try to move those surfaces, they would not be fitting. And we can then have a fully constrained situation. And this is the situation that you're going to be coming across most often, because it's going to be your urban places, it's going to be your beach with an additional pier as well as the cliff. Your railway may have bridges and road signs and so on, and your general residential streets all have lots of lovely tri-directional surfaces which will create a fully constrained point cloud for you. So if we look at what those point clouds need to provide to us in the overlaps that we have, it's got to constrain 6 degrees of freedom. So it's your position, your level, and your orientation are all coming from that overlap. So these surfaces, they don't need to be perpendicular, but it's helpful to think of them in that way. And they can be placed objects in your scene. So where you think you may be lacking in these perpendicular surfaces, you can put your cars in there, and you can use your crashed cars. But when we really look at the good survey practice, what we'd like is a nice long baseline, so that our surfaces are not just in one clustered location. It will still work, but we will get the better survey results out of it having a longer baseline and being that little bit further away. Having said that, we don't really want to be relying on things which are too far away, because then our definition on those surfaces becomes quite poor. So it's not just about the tri-directional surfaces, although they are the one thing that will definitely make it not be confident in the results, but those things which form those surfaces need to be hard surfaces. So if we take a look at the little kind of country road that we've got here, yes, we've got vertical hedges, but those hedges are so fuzzy that the normal directions are in all sorts of different directions as you go down that hedge, and we can't really be sure and consistent of where they are as they blow about in the wind. They're different from one setup to the next. We'd also like 30% overlap between our clouds, and we need, as I said previously, a decent definition on those surfaces. So the point spacing needs to be somewhere along about 5 centimetres for it actually to be useful. And low cloud noise, and of course our initial alignment, if that's good, then it means that the cloud to cloud has got a better chance of coming together as well. So for those instances where we can't have those tri-directional surfaces, or if you're just not sure, then targets can provide us with an extra bit of security. Like with the cloud to cloud, we would like our targets to have a reasonable baseline, so we take them outside of our scene usually, possibly popping one on the top of the crash cars as well, because you get a good line of sight to those. We would need a decent definition on those targets, but you don't need to do specialized scans as long as those targets are within the kind of the range of that scanner to get the appropriate point spacing. So if you do say a 3 mil at 10 meters scan, you could put your targets 16 meters away, and they would still have a good automatic recognition in software to pull out those target centers. So why use targets? As an accuracy check to give you confidence in your cloud-to-cloud results. They are complementary technologies. We're not saying use one or the other. You can use both. You don't need a specialized scan to use them. It's a belt and braces approach. It's your get out jail free card whilst you are not confident if you are not confident in your assessment of your tri-directional surfaces in your overlap. So hopefully that was vaguely understandable. We're here to answer your questions, and I will just hand over to Mike for a summary.
Thanks, Kate. The three people on the call, as I said, it's myself, Chris Gibbons and Kate Strange. I've put the email contact information and mobile phone numbers on there as well if you want to take a note. Firstly, thanks to Chris, thanks to Kate for that excellent overview of best practice for laser scanning in those different environments. Hopefully it's provided everyone on the call with a demonstration of best practice. As I mentioned at the beginning, it's very much manufacturer agnostic. This is simply best practice for all laser scanning techniques. Hopefully you found it interesting. Hopefully you've increased your knowledge perhaps a little bit in the way in which you're approaching the laser scans at various scenarios. But as I said, we are here to help and support as and when necessary. I'm very passionate about ensuring that all UK police forces and officers working within traffic collision investigation are meeting a competency level that allows them to make use of the scanners and the software and provide the deliverable necessary for court purposes. And as I said before, this really all forms part of the validation process going forward. So thank you for your time. And as I said, if there are any questions, I don't see any questions that have popped up for me here at the moment. But if there are any questions, if you would like to email either myself, Chris, or Kate, I'm sure we will we'll come back to you very quickly with the relevant answers. But thank you for your time, and hopefully
Mike,
you have
I think there are some questions.
Oh, are there?
I think
Apologies.
so.
I do not seem to see them here, I'm afraid.
I can see one that says, I've got a question for Kate. Oh, this is quite difficult to read. 1 second. The issue with the second scene, as with the high-speed carriageways, is the number of scans required in order to attain the point cloud density, therefore making it, in essence, not workable due to the final size of the point cloud to then work with. I'm assuming that that means that the number of points is the issue here after you've taken lots of scans, and therefore you're having trouble in a downstream piece of software. There are abilities to decimate the point clouds, and there are also specific pieces of software such as the MAP 360 CAD interface, which allows you to put the point clouds directly into that CAD environment to do your drawings from. I'm sorry if I've misunderstood what that question was about, but I think that was what it was. That there are other softwares available to do the further drawings in, which are happy to deal with a lot of points, but equally we can thin those points out as well.
Kate, I also have another question here. It says, are asking, are the targets the same as we currently use with the C10?
Your C10 will probably have blue and white targets, so a retroreflective blue and a white internal panel. Those obviously are good for the C10 and work brilliantly with that. However, a lot of manufacturers can't utilize those targets, and also our newer scanners don't use those either. The more commonly used ones now are black and white ones. They still have the same tilt and turn mechanisms, but have a black and white surface. The retroreflective of that blue on the outside means that they can't be used so well as a target with the newer scanners or other manufacturers' scanners. You can also use spheres as opposed to tilt and turn targets, and there are automatic extraction functions for spheres as well. And the spheres generally work with most of the laser manufacturers.
Thanks, Kate. Another question that's come through. If we don't have the 6 direction surfaces, how do we practically resolve this on a rural scene?
The utilisation of targets or the placing within the scene of other objects, such as parking your cars across the road to form that additional surface for the alignment.
Okay. And another question here, what size targets are suggested? As with Regal, we don't have any.
The size of the targets, they tend to be around 4.5 to 6 inches in size. Obviously, the main thing is getting the definition on the surface. So the range from the scanner that you put your given target or sphere will depend on the point spacing that you're using more than anything else.
Thanks, Kate. That's all the questions that I actually have here. Apologies for missing them earlier, but hopefully we've been able to answer those questions for you. As I said, if anybody has any further questions or any comments or wants to know more about cloud-to-cloud alignment or laser scanning in general, then by all means, please contact us. I will also make this webinar available. We have recorded it, so it will be available, and I'll distribute that accordingly. So thank you again for your time. Hopefully it's been useful. Hopefully it's provided a good overview and oversight of the use of laser scanning in rural, semi-rural and urban areas. And yes, thank you again, and I hope you all have a very pleasant day. Thank you very much.